Heisenberg uncertainty principle can be stated as follows. It is impossible to know a particle's exact position and velocity simultaneously. Usually it says momentum. What does that mean? Well, think about it. If you're looking out of a window, and outside the window, you have a street, and on this street you have a car. Now, if you have a radar on you, you can tell the speed of this car. You can tell its location at a given point. You can really calculate from the radar speed where it is at and its speed at the same time. Now, unfortunately, when we talk about the electron, you are limited to one of those parameters. You can know the speed or the velocity, the momentum, but you cannot know the location. Or you can know the location, but you cannot know the speed. And think about it. If you don't know both, you won't be able to predict its location or where it's at. Think about it. If you know the speed of something, but you don't know where it started at, you don't know where it's going to be next. If you know the location, but you don't know the speed, you aren't going to be able to predict where it's going to be next either. So this is the problem with quantum mechanics. Is again, this is where determinism falls apart. So if you look at this right here, you might think, if I were to ask you how many electrons are in here, you might say 1,000, 1,000,000, so on and so forth. No, the answer to this is you only have two electrons. You're going to say, what? Well, this is why we need to move away from the idea of just a particle. And that's why you have to watch that video. And notice that this is actually much more complicated. You actually have a probability here. And if you take data points, you'll see that the more dense it is, like here, you're more likely to find the electron. The less dense is you're less likely to find the electrons. Which finally brings us to the most important part of this lecture, which is Schrodinger's quantum mechanical model. So Schrodinger and Heisenberg, all of those physicists are on the par of Einstein. He described electrons as three-dimensional stationary waves, or wave functions, represented by the Greek letter psi. This is psi. So he said those are wave functions, because the electron is not only a particle, but it can be a wave too. Max Born proposed an interpretation of the wave function that is still accepted today. And make sure you understand what this says. Electrons are still particles. And so the waves represented by psi are not physical wave, but instead are a complex probability amplitudes. Okay. So I don't know why this keeps. Okay. So what it's saying to you is, instead of you just believing that you can determine where the electron is at a given point, it is better for you to just simply say, okay, I'm going to use a probability and based on the energy of the electron. And based on its energy, I can say, okay, it's likely to be in this region of space. So again, instead of saying where it's exactly at, we're going to say no. I'm just going to say probabilistically, it's going to be in this region of space. Of course, using advanced mathematics, but we don't need to worry about the mathematics. So wave functions can be used to determine the distribution of the electron density. with respect to the nucleus in an atom, in most general form, this is the Schrodinger's equation, one of the most important equations in all of science. And the quantum mechanical model only gives the location of the electron in terms of probability. But this model enables scientists to determine accurately the energy of the electron in multi-electron atoms. And this is very important. Knowing the electron's energy is much more important than knowing its precise location. We could care less about its precise location. If we know its energy, that is enough for us to use the Schrodinger's equation to determine what we call the probability density, where it's likely to be found. This is a very important definition, so make sure you know it. It's called an orbital. It's a region of space based on a mathematical wave function. It's a region of space where the electron is likely to be found. I'm going to use an analogy for this. Just a quick analogy, because this is really, I understand it's fascinating, by the way. When I learned this in undergrad, I was just taken aback by how really, really intricate this theory is. Imagine, so here's the school you're at. Imagine someone calls home and asks for you. They're going to say, whoever answers the home, here's home. Let's say let's say I have Mary. Someone calls her house at 8 a.m. and asks for her. Let's say her mom picks up the phone and says, "Can I help you?" They say, "May I speak with Mary?" She says, "No, she's not here." Well, let's say this person who wants, really, really, really wants to talk to her, like a friend of hers, or a very important case. They say, "Okay, well, can you tell us where she's at?" She's going to say, "Oh, okay, she's at school." Let's say the name of the school is, I don't know, Chicago School or Chicago College or something like that. So she's going to say she's at the Chicago College. Okay. Does her mom know exactly where she is at inside the college? Well, let's say she knew that this college, for example, has multiple buildings. Let's say she knew she's in building A. Fine. But then even building A itself has rooms inside it. So she wouldn't even know the classroom. Even if she knew where the classroom is, let's say the classroom is 328A or A328, Mary could be sitting anywhere. She wouldn't know where Mary is sitting. Okay. At given point, Mary might have stepped out to go to the washroom, whatever it is. So again, the idea is, imagine the college here is this location, is this orbital, this region of space, and the only thing we can say is, based on the time, imagine that's the energy. Okay, the Mary is likely to be at Chicago College. So based on the energy of the electron, it is likely to be in this orbital. That's all we can tell. That is all we can tell. Which gives us a set of quantum numbers. If you derive the mathematics, the calculations show that the size, shape, and orientation of space of an orbital are determined to be 3 integer terms in the wave function. These integers are called quantum numbers. So let's begin with the quantum numbers. The first quantum number is called the principal. Make sure you know the name of each number, not just the letter, but the name as well. So this is called the principal quantum number, n, and it indicates the energy of the electron or the size of the orbital. And all this is that n can be a positive integer. So n can be 1, 2, 3, 4, 5, 6, all the way to infinity. Just know that n in this case is the energy level. So if I have n equals 1, we call that the ground state, or our first energy level. If I have n equals 2, this is called the second energy level. What do you think the third is? 3, third energy level, so on and so forth. Okay. These are usually called shells as well. So we call this the ground shell, or just the first shell, second shell, third shell, so on and so forth. Energy level and shell are both acceptable. Energy level are more common, especially at this level. One thing I wanted to add before I move on is that the period number in the periodic table, that's n. N, okay, is the period number. So if we have a periodic table right here, that's your n right there. N equals 1, first energy level, second, third, fourth, etc.